Hello everyone, welcome to the 7th lecture. So this is singular value decomposition / principal orthogonal decomposition part 2. I hope everybody took a look at the first part of this lecture that was only recorded. Sorry? Yeah. Is it working? Echo? I have an echo. I'm not sure if I can fix that. Is it really bad?
Yeah, it's very good. So, you need to go to the...
Okay, we have some technical difficulties. We're trying to fix this. Because I only have... Oh, okay. I think I disabled that, but maybe it re-enabled. Yeah, I did. Okay. It's very strange. I think there's still 4 cells still active. Okay. I hope that's better, and else I'll probably get immediate feedback again. Okay, so I was saying last week I had a recorded lecture because it was a holiday, and I still wanted to give you the necessary material for the project. Now that was still already,
It's still the same.
Same echo problem. I only have one audio. Is Hua having the same? Are you also getting echo?
No.
Well, maybe it's because you have it open on 2 channels.
No. But if you don't have echo, then it's fine.
So you don't have echo?
No.
Okay. Thanks anyway. Okay, I think everything might be fine. We'll see. Yeah, so as I was saying, last week we had an introduction to this stuff, everything that was needed for the project. And now I want to go into a little bit more depth on this aspect. And I specifically want to talk about really what is the difference between the singular value decomposition and the principal orthogonal decomposition. Because so far I've kind of talked about these as if they're the same thing. And we'll talk about what the difference is. And I can already kind of tell that a little bit. The singular value decomposition is really something that exclusively focuses on matrices, as any array of numbers really. So it's an outright decomposition, and it works in all kinds of cases if those numbers have nothing to do with each other. So POD takes that and kind of realizes that every column that we are interested in, well, it carries a meaning, right? It's not just an arbitrary set of numbers. It encodes a function in a finite element setting. And it uses that information to do this decomposition a little better. Yeah? So that's what we'll see today. So that's really building on top of the lecture from last time. So I'll first give a little bit of a recap about what we talked about then. So, recall. The problem that we're trying to tackle is a parameterized partial differential equation. Some differential equation that depends on a set of parameters, and that partial differential equation carries a solution which then again depends on those parameters. And we said we can define a solution map that maps from our set of parameters onto our finite element approximation space UH. And in the language of the function spaces that we've been using, that would be a subset of H1 on some domain omega. Yeah? So here it is P, that is the set of all possible parameters that we might consider in a parameterized partial differential equation. And for each such parameter point, we have some finite element solution, which is at this point still a very highly expensive computation.
I'm very sorry for the interruption,
yeah?
But maybe it's important for you. Only 2 people are watching, and it's one.
I'm also recording. Okay.
Did you upload this so that we...
How did you get access?
I got it via the link. It should have been.
Yeah.
Should be fine.
I suppose that people are going to join in a minute, else I have to record it version. Okay. And this solution map that takes a parameter point in our parameter space and it maps to some output function in our finite element space. And this is a very expensive map, and that's the objective of the reduced order model, to make an approximation of this map that is cheap. So we had some additional nomenclature. we talked about the solution manifold as all the possible solutions in H1, and specifically in this UH, our finite element approximation space, that can possibly be mapped to by any parameter point. So if we map all the parameters in our parameter space using our solution map, then we produce the solution manifold. So this is the solution manifold. Okay, and then what we said with POD and SVD, what we're going to do is we're going to sample our solution manifold, and we're going to try and approximate this complete solution manifold by a whole bunch of sampling points. And the set that we could introduce to describe that would be S, that's the snapshot set, because every sample, every solution corresponding to a sample is called a snapshot. So the snapshot set is, well, the solution map phi of, well, a number of snapshot parameters. Yeah, so that's not completely all of P, not a complete parameter space, but it's a bunch of snapshots, or a bunch of parameter points in that set. So we're calling this the snapshot set. Where, again, to specify this a little better, where P and S would be some set of parameter points in our parameter space. And how many are there? Well, we have going from 1 to ns. Yeah, so ns is the number of snapshots. Now, what kind of subset is this? What we have to realize at this point is that every entry in our snapshot set is a function. Yeah, this is a function of space, it's a finite element solution in terms of a function in space. So this is some entry of UH to the power of NS. Yeah, this is a collection of NS functions in UH. And this is already kind of showing the disconnect between SVD and POD, because for POD it's really this representation that we're interested in. We know that each of these entries in our snapshot set are functions, whereas SVD focuses on arrays, right, matrices. And there is a strong equivalence, because of course we can define our snapshot matrix, which I'll write as a double S, as some entry in R n times ns. And it's because this solution in UH is encoded by a number of coefficients that are multiplied by basis functions. And so this is what we're calling the snapshot matrix. And again, we can do this because for every UH in our finite element space, we can write UH as the sum going to n, the number of bases, of some U hat I times the corresponding basis function. Yeah, so these UHs would be the ones that are in our snapshot set, and these guys, the values of the basis functions, are the ones that go into the matrix. And they're encoding the same thing, but of course if we don't make this connection, then by itself those values, the values in the snapshot matrix have no meaning, right? So it only has meaning once we connect it to a basis function, then it defines a function. And that's in the end what we're really interested in. We're not interested in any of the numbers in the matrix, we're interested in the solution as a function of space. So that distinction is going to be important to make the difference between SVD and POD. So then, jumping right into the singular value decomposition, that was based on the snapshot matrix. It's a matrix decomposition. So the singular value decomposition looks as follows. We take our data matrix S, which is of size n by ns, right? The number of degrees of freedom, which might be 10 million, the number of snapshots, which might be 1,000, 10,000. And we're going to decompose that in an orthonormal matrix U, a diagonal matrix sigma, and an orthonormal matrix Z. And this one is transposed. Now, in order for these, so these two are orthonormal. And this guy is diagonal. And importantly, decreasing. So every subsequent value on the diagonal is smaller than or equal to the previous one. So for these matrix sizes to add up, we have to begin with the big N, we have to end with NS. Well, because the first and the last are orthonormal, they have to at least be square. So these are big N and NS, which already shows that the central matrix goes from N to NS. And I had some illustrations of that for the two relevant cases. That's this guy. Sorry. Yeah, so this is kind of showing what the matrix sizes would look like if you would compare the different matrices. And the relevant one is the one on the bottom, right? Because typically we have many more degrees of freedom than we have snapshots. So the first one is, in that case, a very big square matrix. The last one is a relatively small square matrix. And the middle one is, well, a stretched matrix, which is diagonal, and we interpret that in the sense that is illustrated here, right? So we only have values when the row and the column are the same. Which means that in the bottom it has a bunch of zeros. Okay, let me also kind of draw that here for that relevant case. So we have a matrix, a snapshot matrix that is standing, where we might have a number of snapshots. That's the number of columns that we have, and n the number of rows. And we have a very big square matrix that is n by n. And we have this standing matrix that is of the same size. That's the diagonal one. So this is U, this is S, this is sigma. And another square matrix that is of the small dimension. Z transpose. Now, okay, again, this is a diagonal matrix, which means that it only has values around here. The rest are zeros. And if we work out the matrix multiplication, that kind of implies that the stuff that's in here is also not entirely relevant. It's just a filling in the sense of making this an orthonormal matrix. So these vectors could always be shifted and it would still carry the same value. Okay, so that's the singular value decomposition of a matrix. And we're going to write these matrices because we're going to be interested in the actual vectors in these matrices. So I'm going to write the matrix U as a collection of xi's, xi1, xi2, running to xi big N, right, with a square matrix. So each of these are big N vectors. And since this is an orthonormal matrix, this means that each of these vectors is orthogonal with respect to the other ones. And additionally, we have that the magnitude of each of these vectors is also equal to 1. And this is true for all I. Then our sigma, we're going to write that as the diagonal matrix of sigma 1, sigma 2, running until sigma ns. One over here. And sigma 1, so this is ordered in such a way that we have that sigma 1 is the largest one, sigma 2 after that, etc., etc. And lastly, our matrix Z is again also a matrix of vectors, and we use a transpose in our notation because then right now I can also simply talk about these as vectors, column vectors, and we have ns of those. And these are also orthonormal, meaning that also each one of these has a unit length. Okay. Then, why was this so interesting? Well, we had this best rank approximation property. And I was saying that, so each of these vectors in each of these matrices, we found that if we work out the multiplication, then we can see that the first vector multiplies by the first row vector in Z to form a matrix that has the dimensions of S, and is multiplied by the first, singular value is what we call that, so sigma 1, and that carries most of the information in that matrix. And the subsequent vector multiplication carries the second most important information in that matrix. So we had this decreasing number of matrices that each carry more or less and less information as we start summing. So the approach to compressing the data set would be to only take a couple of these matrices as opposed to all of them. So we only need to store a couple of these vectors. And I had an illustration of that as well, where we actually talk about this in the sense of image compression, right? Because we can think of an image as a matrix. Each pixel has a value. So that would be our snapshot matrix. And what I can do then, I can do an SVD on this data matrix, and I can only take the first couple of vectors in the first couple of columns. And if I then use that matrix multiplication, then I find that the first mode is, this image. And if I add the second mode to that, or in this case the first 5 modes, if I add all of those together, then I get this image. And so I can add more and more modes together to capture more and more of the information in the picture. Now, so this is already illustrating the compression nature of that of the SVD algorithm. So to write that in a more formal way, that is that we can construct the best possible rank K approximation as follows. So we have the best rank K approximation of S, of our snapshot matrix, as a new matrix, as tilde, which we'll write not as the complete U multiplied by the complete sigma multiplied by the complete Z, but instead by only the first K column vectors in U. So we have 1 until psi K, multiplied by a matrix that carries the diagonal components sigma 1 until sigma K. So also not all of them, but only the first K. And this is multiplied by a compressed version of the Z matrix as such. And this notation is a little bit confusing, but if we work out the matrix multiplication, then we see that this is saying nothing more than that this is a sum from I is equal to 1 until K, so we have K of those, rank K, of column vectors psi I multiplied by scalar values sigma multiplied by row vectors zeta transpose. So each of these is a matrix. If you work out the multiplication, this is a matrix of size n by ns. Yeah? So here we have n by 1. Well, this is a scalar, so this factors out. And here we have 1 by ns. And so each of those is a matrix, and if we add them together, we get more and more information. Now, one additional comment that I made is, this is already very clearly showing the capability of compressing something, and it's actually getting better than this, because in a picture, all of the columns, they could be completely different, right? There's no relation between the first column of pixels and, the 100th column of pixels. In our case, every column is roughly the same. Of course, we have this parameter dependence on our solution, which shows up in the different columns. But we might not expect completely varying distributions of data. So the more relevant comparison, as I continue then, was to say, well, actually, every column should roughly capture the same data. So what we can do is, for instance, fill a data matrix with pictures. So I took a whole bunch of pictures from our website. I compiled those into a data set. So now every picture represents a column in our snapshot matrix. And if I then perform SVD, then the first column that we obtain from the U matrix, that represents the singular faces of this data set. Yeah, so that looked then something like this. And so they are very much related to eigenvectors and eigensolutions, and we'll actually make that connection in a second. But right now, this is not an eigen problem yet, because well, we're not dealing with a square matrix, so that doesn't exist in that sense. Okay. Now, and I think this is kind of where I left off the last time. I would like to make an additional comment to this point, because this is still a little bit vague, right? The best approximation, what does that mean? We have to have some definition of what is good and what is bad in order to make a claim about this being the best one. And the way that this is best is in a certain norm. Yeah? That's the way that we measure errors, that we measure differences, so that's how we distinguish or determine if something is best, by measuring the norm of the error. And the norm that is taken here, that's relevant for this case, is the Frobenius norm. And that is the following. Well, I'll first write down the norm and then we'll get to the statement. So the norm for any matrix, the Frobenius norm, is defined as the sum over all its different components, or its different values. Oh, it should be 1, of course. 1, 1, going to n. And then we're going to square each of the values in that matrix. And then we take the square root of that. So this is a Frobenius norm. It's sort of, yeah, you can look at this as this has relevance for these squares, of course, as we'll see actually for this example. And just to be clear here, our matrix A is in our m times n. Okay, so we can make a statement about this best rank K approximation in this norm. And that statement reads that if we take now the Frobenius norm of the error that we're making with this rank K approximation, so we take a complete snapshot set, we subtract our rank K approximation, and we take the Frobenius norm, then this error is equal to the minimal possible error that we can actually make given a matrix B of the dimensions that we're looking at, where the rank of B is equal to K. Yeah? So what this is saying right now, that the matrix that we obtain by doing this truncation of our singular values and singular vectors, that is the best approximation given any possible rank K matrix in the Frobenius norm. And it gets even better than that, because we actually get an expression for this error that we're making in terms of the singular values. Namely, the error that we're making here is the sum of what I is starting from actually the next component. So we go from K plus 1. Yeah, so we created this sigma tilde by taking the first K components. Now we're going to take all the other components and sum the singular values squared. So by doing this, we get the best possible approximation to our snapshot matrix in this measure of what is good. And specific, even more specific, we can already, in an a priori sense, without doing any further analysis, we can already explicitly say what that error is going to be. It's going to be the sum of all the remaining singular values. So this whole notion is called the Schmidt-Eckart-Jung theorem. Now clearly that's a very powerful tool, because what this allows us to do is beforehand, when we are constructing our reduced basis method, already at that point we already know how many bases we should take into account in order to ensure that our error that we will make with our reduced basis method will stay below a certain bound. Now at this point I'm assuming that the snapshot matrix that we have is a very, very good representation of the complete solution manifold, and that's the assumption that I'll keep on making for the entire lecture. Yeah? So we'll revisit that assumption in later lectures. For now, the snapshot matrix is a very, very good approximation to any possible solution that we would get for our parameterized partial differential equation. Yeah, so this seems to be a very, very powerful setup right now. Yeah, we have a tool for creating our reduced basis method. Yeah, the reduced basis that would be interest to us would actually be these components, right, the xi's. We have a statement that this is the best possible approximation, great, and not only that, we actually know the precise error that we're making. So this seems to be a really, really good setup. But now I want to address the point that I already kind of hinted at the beginning, and that is the question, is this really the relevant norm, the relevant solution error? So is that the Frobenius norm, is that the relevant case? Is that relevant? Now, at first it might look like this is an extremely powerful statement, this whole setup. But now I would like to think about that what this is really saying. It's giving us the best approximation in the sense of the square of the different nodal values, the different coefficients in our solution vectors. And clearly that is already something, but I would maintain that that's not entirely what we want yet. Yeah, we start off making exactly that point. That's really a solution vector of a finite element computation by itself doesn't mean anything. Those two values in that vector, they only have a meaning once we connect that to the basis. Yeah, for Lagrangian basis functions we know that these values actually represent nodal values, but in a sense that is a coincidence, and there are many, many cases of basis functions for which that's certainly not the case. More importantly, even if we consider these Lagrangian basis functions and we take them as these nodal values, if we have a large element, shouldn't that carry more weight in this optimization property than a small element, right? If we make a mistake in a large element, that should have more of an impact on our complete solution than if we make a mistake in a small element. Yeah, so we somehow want to incorporate in this setup the information that those solution vectors are really carrying in the sense of the solution that they encode, the finite element function. So not only look at the values in the matrix, but really think about what they mean. Yeah, so our objective from now on is going to be to edit our scenario, our SVD, in such a way that these become meaningful norms and meaningful optimizations. Yeah, so what we really want is we wish to get optimalities in norms that are applicable to us. Yeah, so we wish to get optimalities and what kind of norms are relevant to us? Well, as I talked about in the first and the second lecture, is that also functions have norms, and they capture the magnitude of a function, and also if you compare two functions, we subtract them, they compare the magnitude of the error that we're making. So we have our own norms that are relevant to our functions. Yeah, so we wish to get optimalities in function norms. And the ones that we discussed were, for instance, the norm that is of relevance to any function that lives in H1. And another one that is also very popular, and the one that we're going to focus on today, is if we want to get optimalities in an L2 sense. Yeah, and just to make this more explicit, suppose that we have some function u of x, then the L2 norm, just as a rehearsal, what was that again? Well, that was the integral over our spatial domain, our 2D or 3D domain, of our function u squared. And after that we're taking the square root. Yeah, so clearly this looks a lot like what the SVD is doing, but the SVD is completely forgetting about the fact that these values in the matrix are not directly the functions, but we have to introduce some sort of change in operation here. Okay, so we're trying to somehow wedge this operation into the SVD. How are we going to do that? Well, first, in order to understand where this might pop up, we have to understand what the SVD is doing a little better. So first, what actually are, I'm trying to combine two words there, what are the vectors that we obtain, psi I and zeta I and sigma I. Well, we had names for those. We called those the left singular vectors. And we called this guy the right singular vectors. And these were called the singular values. But how do we actually obtain those, and what do they actually mean? Okay, let me rewrite the SVD here, and then we'll get to that, because actually we can define a different problem that we're more familiar with that actually encodes these guys. So again, we have a snapshot matrix S, which is equal to U sigma Z transpose. Now I want to get an understanding of each of the vectors. Well, let's start off with each of the vectors in U. What I'm going to do is I'm also going to obtain the transpose of this snapshot matrix given this representation. So what's a transpose? Well, the way that you would obtain a transpose of a series of matrix multiplications is that you would reorder the shuffling of the matrices, you would reverse that, and you would take the transpose of each of those matrices. So what does that end up saying? Well, we're going to start with the Z now. We're going to transpose that. Well, it was transpose. Then we have this sigma transpose, and we have U transpose. So let's now consider the multiplication of both of these guys. Yeah, so we're going to multiply S by S transpose. So what kind of matrix do we end up with? Well, this one had a dimension that started with N. And the other guy, well, that's the transpose of that, so it ends with N. So we get a very big N by N matrix, right? Maybe 10 million by 10 million. So this is the multiplication of this U. And, okay, forgive me, but from now on, I'm not going to try and write that all in this double case. That's going to be very tedious. I hope that it's clear that these are all matrices, right? And probably I'll maintain doing that with the S because I don't want to make the disconnect with the set of solutions as opposed to the snapshot matrix. But for U, the sigma and the Z, I'll stop with that. Okay, so we have U sigma Z transpose multiplied by Z sigma transpose U. Well, by definition, our Z was orthonormal, which means that this guy becomes an identity. So the multiplication that we're really looking at, and sorry, this should still be transpose here, is U sigma T UT. Now this is something that we recognize, and this is something that I addressed in last week's lecture. Let's see if I can quickly put that up. Let's go out of that, go in here. Because when we talked about different cases of matrix decomposition, we saw, well, the last one is right now the one of importance, that for symmetric matrices, we can decompose using the spectral decomposition as an orthonormal matrix V of eigenvectors, then a diagonal matrix D of eigenvalues, and the orthonormal matrix of eigenvectors transpose. And that is precisely what we're seeing happening right here. Yeah? So if we collect this, this also becomes a diagonal matrix, which starts with, well, sigma 1 square, then it goes to sigma ns square, and it still has a whole bunch of zeros on the end, because again, this is now an n by n, a very big matrix. The first ones are filled, the last ones are not, but still, this is a diagonal matrix. We have an orthonormal matrix sitting up front, and we have to transpose over an orthonormal matrix sitting in the back. So what we see right now is that U is actually a combination, is actually filled with the eigenvectors of this S transpose. Yeah, so how do we recognize this? Well, this is precisely the spectral decomposition of the symmetric matrix ST. Yeah, so clearly if you multiply a matrix by its own transpose, it becomes a symmetric matrix. Yeah, so again, this is symmetric and square. So the conclusion from that is that each of the vectors in U is actually an eigenvector of that matrix. So each of the psi i's is an eigenvector of ST. Well, more than that, we actually also know now that each of the sigma 1 well, squares, right, there's a square in there, that all of those those are the eigenvalues of S transpose. Well, and the fact that we end up with a whole bunch of zero eigenvalues, that's not an issue, and it also makes sense because we had a thin matrix. We're creating S transpose as a very big matrix. Well, clearly that very big matrix cannot contain more information, and that's captured by the rank of the matrix, and that is also shown by that there's a whole bunch of zero eigenvalues in there. So that's not something we worry about, that makes sense. Now let's see, I think we can do the same trick, but now in reverse. So we're going to consider the matrix STS. And what do we get if we carry out the matrix multiplication? You would get Z times sigma T times UT times U sigma Z transpose. I can already see what's going to happen here. This is again the identity because these were defined to be orthogonal matrices. So this is also a spectral decomposition, but now involving the Z matrices. And this is now the matrix, the diagonal matrix, that only has sigma 1 square going to sigma ns square. Yeah, because this is actually an ns by ns matrix. So we can make the same point. This is clearly the spectral decomposition of the matrix, which means that any of the psi vectors are eigenvectors of STS. And additionally, also the sigma I squares are eigenvalues of that same matrix. Yeah, so interestingly, the sigmas, they show up as the eigenvalues for both of those matrix computations. Yeah, and in a sense that makes sense because they carry similar information. Okay, the final connection that I would like to make is if we again take our singular value decomposition as it's staying right there, what I can do is I can post multiply everything by Z. And that cancels the Z transpose Z on the right because that would be the identity. So finally, what we can also do is S times Z, and then we would get U times sigma. And similarly, I can pre-multiply everything by U, or the way that or U transpose, and then transpose everything, and you would get ST times U is equal to Z times sigma transpose. Now what do these things mean? Well, they actually show a connection between the vectors that are in Z and the vectors that are in U. So they show a connection between the left singular values and the right singular values as vectors, in the following sense. The matrix S multiplied by any vector zeta is going to be the same thing as sigma I times psi I, and S transpose multiplied by any psi I is going to be equal to sigma I times zeta I. Yeah? So each of the singular values is represented by an eigenvalue problem of the matrix made square, and they also relate to one another with these two rules. Okay, so this is the base information that we need, and at this point we can start to tinker with the setup. Yeah? Where, again, our objective is to sort of wedge the function norms in our definitions as opposed to this funny Frobenius norm. How are we going to do that? Okay, so the trick lies actually in this second eigenvalue problem, St times S. Because if I work that out, what does that matrix multiplication actually say? So I take St multiplied by S. So this is a number of snapshots. Recall, each of the columns in our matrix is a solution vector of some parameter point. So I'll just call this U. And I'll underline them because I again want to make the distinction between the arrays or the vectors of coefficients and the function themselves. These are now the vectors of coefficients. U2, going all the way to U, number of snapshots. Well, this guy was transposed and we're multiplying by the same thing. And each of these are vectors of coefficients. So if you work that out, then you find that, well, the first, the 1, component of S transpose S is going to be the first row vector, which is U1 because we're transposing this, multiplied by the first column vector, which is again U1. And so the first component in this matrix is going to be U1 transpose U1. And we can carry this multiplication out for each of these components, and then we would find that you have a structure that looks like this. Yeah, so we're multiplying each of the values in this matrix is a multiplication of a lying vector multiplied by a standing vector. Well, that is actually precisely what a dot product does, right? So let me make that explicit. So this is really U1 dot U1, U1 dot U2, U2 dot U1. So clearly this is symmetric, right? The dot product is invariant to shifting the multiplications. And I again want to be explicit, these are all vectors of coefficients. And this is already actually something that we can start working with, because what was a dot product? Well, the dot product was the inner product that is relevant for the space of vectors of Rn. Yeah, that's the inner product associated to that space. We have our own inner products. We have the H1 inner product, the L2 inner products, and those are the ones that are relevant to functions. Yeah, so this is a stage where we want to change the operation from a dot product, an inner product between vectors, into really something that encodes the inner product of the associated functions. Now, before I do that, I kind of want to still make the one connection with data science here. This is called the correlation matrix. In a general data set. And it already also connects to that inner product idea, right? We talked about inner products in a general sense as measuring, well, I called it angles at the time. I would say right now, I would say they measure similarity, right? So we have the notion of orthogonality if two things are completely unsimilar, and that means that the inner product is 0. And if two things are very similar, namely they're parallel, then the inner product leaves the magnitudes of those guys multiplied by each other. Yeah, so in this sense, this correlation matrix is capturing all the similarities between the different components in the data set. Yeah, and that's why it's capturing exactly the important information. Okay, but again, it's making that, it is measuring those similarities in the wrong way. We're not interested in inner products between arrays of nodal coefficients, we're interested in inner products in L2, for instance. So this guy is filled with R big N inner products. Okay. So this is where we're going to introduce meaningful inner products. So here we introduce meaningful inner products. Is meaningful a double L? Not sure. Think not. Okay. So I'll put a squiggly line under meaningful because obviously that's a bit of a vague term at this point. So let's make that explicit. The one that we're going to be interested in is the L2 inner product. The L2 inner product. So we have a function u of x and we have a function v of x. And this is how we write the L2 inner product of those functions. Now what was the explicit operation? Well, that was the integral over the complete domain of u of x multiplied by v of x. Yeah, so this was the L2 inner product. You can also see that if u of x and v of x are the same, well then we get the norm squared. So this is the one that we're going to use, but just to give you a bit of a refresher, and recall also that the space of h1, all the functions in L2 that have one well-defined derivative. We also have the inner product for those guys. So suppose that we have u of x and v of x and they both live in h1. Then we can take the h1 inner product. And how was that defined? Well, we take the inner products of these guys in L2. And we're going to sum to that the inner products of the gradients of those guys. Also measured in an L2 sense. Yeah, so clearly this gets more and more complex as we continue up the ladder. The one that we're going to focus on is this one, because this already very clearly captures what we're trying to do. This is sort of, we're trying to get the best least square approximation in an integral sense, as opposed to in a sampling of point value sense. Yeah, that's what this is really doing. So we're trying to wedge in this inner product as opposed to simple vector inner products. How do we do that? Well, the thing that you have to realize at this point is this inner product is really nothing more than a new bilinear form. And it's a bilinear form that takes functions, well, in general functions in L2 that we can square and integrate. But the ones that we're interested in actually live in that finite dimensional finite element approximation space. Yeah, so each function that we are going to be interested in, so each function ux can be written as a sum of coefficients times basis function in space, right? And similarly, every function that we might put in the right slot, vx, can also be written as the sum from I is equal to 1 to n of coefficients v multiplied by the same basis. So compared to the vectors that we have right here, you would write this as u transpose vector times now a vector of basis functions nx. So now these are the vectors that we were familiar with in finite element computation. And similarly we have a vector v, which is filled with all the coefficients, so these are all the v hats, multiplied by n, a vector of basis functions. So we can really proceed in very much the same way as we usually tackle these bilinear forms in finite elements. We're going to substitute these guys and we're going to pull them apart into a matrix multiplication. Yeah, that's exactly how we obtain a stiffness matrix. So what do you get if we do that for this guy? Well, you actually get something that, well, maybe you already, well, you should be already familiar with. I'm not sure if you've already seen that right now. So suppose that we interpret this inner product as this bilinear form that again takes two functions, u of x and v of x. It's going to be the integral of u. I'm going to flip this around, so I'm going to say v. Is that important? Yeah, I'll do that. So I'm going to start with v transpose n, vector, vector, n of x. And well, I can, of course, this is, they're all scalar functions, so I can flip the multiplication and I can say nt of x u. Well, the v and the u, they're vectors of coefficients, they're independent of space, right? So I can pull those out, and then you get a vector up front. You get the integral of nx and transpose x and a u in the back. And I hope this is familiar. This is going to be a matrix of dimension n by n. And please excuse my reuse of letters at this point. This n is again the number of degrees of freedom. And this matrix, we have a very common name for this. This is the mass matrix. Yeah? This is the matrix n. The mass matrix. So what this is saying is if we're interested in taking the L2 inner product of two functions, ux and vx, that both have this finite element, that both live in this finite element approximation space, then all we have to do is pre-multiply the mass matrix by a transpose vector and post-multiply it by a standing vector. And this encodes now the L2 inner product of those functions represented in our finite element space with these coefficient vectors. And that is something that I already addressed in one of the homework assignments, so I'm hoping that you recognize this. I think that was in the modal decomposition one. Yeah, okay, it's already popping up right here. So that's precisely equation 10 and 11, right? Where we're taking the L2, and in this case we're taking the L2 norm, which is the same thing as taking the L2 inner product, but filling in the same function two slots, and then still taking the square. So that's why there's a square in here. And you see that is precisely the vector of coefficients transposed, multiplied by the mass matrix, multiplied by the vector of coefficients. Yeah, so that's exactly what this is saying. So you've seen this before. Okay, so what was now our objective? We wanted to replace this correlation matrix, which was a combination of inner products in terms of vectors of coefficients, by inner products in terms of functions. So we want to put this mass matrix in there, and we can actually very explicitly do this, because if I literally put a mass matrix in between the S transpose and the S, and the way that the matrix multiplication works out, you would get, so if I put the mass matrix in here, you would simply get the mass matrix in between all of these guys. And that is exactly what's giving you now the L2 inner product. Yeah, so at this point my notes are not very linear anymore, so maybe I'll add an arrow. There we go. So, okay. So that is exactly what we're going to do. So here we want to introduce meaningful inner products. To connect back to that, so the relevant correlation matrix is S transpose times the mass matrix times S. And just to be clear, this is going to be ns by n, this is going to be n by n, this is going to be n by ns. Yeah, so we still get ns times ns as our final multiplication size. So that all fits. And the relevant eigenvalue problem is St ms is equal to, well, the relevant, maybe I should say the relevant spectral decomposition. I think that's probably a bit clearer. So we have a new matrix Z. I said I wasn't going to use the double quotes anymore. with new sigmas, another Z transposed, and to make sure that it's clear, these are different compared to the ones that we had before, right? So bar, 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 bar. I'm going to add bars on top of those. Those are different matrices, but they will take over the role of this spectral decomposition that we had here. Yeah, here we have the spectral decomposition of the correlation matrix S transpose S is equal to Z, sigma, sigma, Z. And we're going to replace that by this relevant correlation matrix S transpose mass S as a new Z, sigma, sigma, Z. So we're sort of enforcing this on the SVD. This is what we want you to do for the vectors in Z. Yeah, so the new Z is now filled with xi's bar that are different from the ones that we would obtain from the pure SVD, because right now they are encoding the relevant information. Now the zetas are actually not, these are zetas, I thought I said xi's. The zetas are actually not the ones that we're interested in for our reduced order model. The basis vectors are the ones that are the left singular vectors, the ones that fit in the U matrix, the xi's. So the last step that we really have to take is we want to enforce this setup onto the SVD. So we want to enforce a matrix decomposition of our original snapshot matrix as a new vector U of left singular values, vectors, bar times sigma bar Z bar, where these guys are the ones that we just computed with the new eigenvalue problem. And now we're interested in finding, given those from the previous problem, these two, given those, what will be the vectors in U? Well, the singular value decomposition is unique. There's only one decomposition in the sense of an orthonormal matrix multiplied by a diagonal matrix multiplied by an orthonormal matrix. So trying to force this may seem a little funny. The conclusion is simply that U is no longer an orthonormal matrix. So this is no longer, this is no longer orthonormal. And actually, Z is also no longer orthonormal, unless I'm mistaken. I think that they might have a different normal property, but I'm not 100% sure about that, so I'll not touch upon that. Yeah, but still, this is going to be, the U is now going to be a matrix of these xi vectors, xi1, xi2, and now all with bars, yeah? Until xi ns. Now, we already came up with a relation between those vectors, and that relation still holds, despite that we changed some things, we shuffled some things around. Namely, I don't know why is it not taking change of color, there we go. Namely, this guy. Yeah, so given that we have now already fixed the sigma, the singular values in sigma as squares of the eigenvalue problem that's written down there, and the Z matrix is filled with zetas, which are the eigenvectors of that problem. Given those two properties, we can now find these xi's as 1 over sigma I bar times the snapshot matrix times zeta I bar. Yeah, where these guys coming from there. Nope. Okay. Then we're almost at the end of the story, because what we're going to do right now is, this is where we define our reduced basis. So now we define our POD, proper orthogonal decomposition, reduced space, Vn, or as Vn right? That's what we've been using as a reduced space, as the span of the first n of those left singular vectors. Well, they're not really that anymore. I'll just call them xi's. The first n xi's. Well, and the span, we're talking about a function space again, so I have to transpose this and I have to multiply this by the vector of basis functions. Okay. Now, so this is going to be a subset of our finite element space. It's going to be the linear combinations of all the functions that are encoded by the vectors of coefficients obtained with this procedure. Okay, so is that a good approximation space? Well, yes, that is the one that we're interested in, because right now we have a new Schmidt-Eckert-Young statement. So Schmidt-Eckert-Young revisited. So the new statement, well, we had a statement about this best optimal approximation property and a statement about the error. So we have a similar statement now in this POD setting, and that is Vn, so this space is the best n-dimensional subspace of U, or UH, to approximate any U inside of our snapshot matrix, or snapshot set, right? At this point we're again talking about functions. So this is no longer a snapshot matrix, this is the snapshot set. Again, recall this was the mapping, the solution map of all possible solution points, P, MS. That is making some noise. And again, best in what sense? Well, now we enforce this L2 property in there, so this is the best one in the L2 norm. Yeah, and that's the relevant case for us. That is the best approximation property. We also had this error property, so moreover, we know now that the sum of all our solutions in our snapshot, if we take the error of the solution in that snapshot, so the function ui in the snapshot, so this guy is in, and we take the error with respect to this reduced basis approximation thereof, and not just that, but the best one, so we take the minimal of U tilde in our reduced basis space, Vn. So this is pretty much the error that we would be making if we approximate any real solution in this snapshot, in this solution snapshot or the snapshot set, and we would approximate that with the reduced basis that we just constructed, and we measure this error in the L2 norm, then this is going to be equal to the sum of all the leftover singular values. And not really singular values because we messed around with the setup. It's no longer singular value decomposition, but really the eigenvalues of this new eigenvalue problem that we set up here. Yeah? And all the leftover ones. So I is equal to n plus 1 going all the way to ns. Yeah, so this is really the properties that we are interested in. Yeah, this is saying, given this changed setup where we wedge a mass matrix into the optimality property or the correlation matrix, we find that our reduced basis space in a POD sense is the best reduced set in that L2 norm. And specifically, we get an error estimate, where we can already say beforehand, if we use a certain amount of bases, this will be the minimal error, or the maximal error, sorry, that we'll be making. Or if I invert that, we could say, I only accept an error that is of this size, well then this is the amount of reduced bases that I should put into my V n-dimensional set. Okay, so this was what I wanted to talk about in regards to the SVD POD. And that's pretty much also where we kind of leave this topic and continue with something else. To already give you sort of a hint what we're going at is, well, this is still really hinging on the assumption that our snapshot matrix is a good representation of our solution manifold. And that assumption is actually a very expensive assumption. If we have a large parameter space and we would need to sample that so finely to make that claim that our solution manifold is properly approximated by our snapshot set, then that's going to be an extremely expensive procedure, even for an offline set. So what we'll talk about next is an alternative to something like that, where we have some measure of the error already, and we can do that kind of in a smarter way. Now, I still wanted to talk about one of the things that was in the project, and that is this statement here, where we're talking about the compliancy of an output. And I think I should talk about two things in this context. First of all, I should actually talk about what I mean by an output, because I really haven't addressed that yet. And then secondly, what is meant by that compliance. And so I'll do that as a finish to this lecture. Okay, so again, we had this offline-online decomposition, and that's hugely important to the complete setup of reduced basis methods, where we had a parameterized PDE as an input, and we have a new parameter point as an output, or in our online phase. And our objective is for the new parameter point to get some sort of output. And this is the setup that we had done. I think I messed up my animations again, we'll see that in a second. And I want to make sort of a change in this setting, because it's not entirely it's not entirely the complete story yet, and that mostly hinges around this very last step, the post-processing step, that's still kept a little vague. So we have to explicitly change that a little bit, and we will do that here. So, yeah. So I changed it a little bit, and I added really only one component, or one aspect, I should say, and that is this guy. And that shows up not only there, it also shows up here, it shows up here, and it shows up here. And what that is our output definition. Yeah, because obviously we're doing these simulations for a reason. We're interested in some property of our solution at that new parameter point. What might that be? That might be if we're talking about an aerodynamic optimization, we might be interested in the drag of the shape that we have been working on. Yeah? So we want to build a reduced order model so that we can quickly recompute solutions for new aerodynamic shapes. And the output that we really want to see is this shape good in the sense of the amount of drag that it produces. So then we have a very explicit output value that we're interested in. And this output value, this depends on the solution, naturally. Yeah, so we have a value as an output and a solution as an input. So what does that mean? Well, that's a functional, right? So we have a functional that we use as our output. It's the output functional. Now, in the whole setup, it was extremely important that everything that we do during the online phase is independent of the amount of degrees of freedom in the offline phase. Yeah, in the offline phase, we're happy to spend lots of computational expense as long as during the online phase, this is all cheap. So we want to be able to assess this output quantity in the online phase in a cheap way, independent of the number big N. And we can actually do this in pretty much the same way as everything else that we've set up so far, because a functional, we already treated this, the right-hand side of a bilinear, or of a weak formulation, the left-hand side is the bilinear form, the right-hand side is the linear form. Or what is a linear form? A linear form is precisely a functional. A linear form is a form that takes in a function and spits out one number. Yeah, so this is a functional, and that's precisely also what our output should do. Our output should take our solution and spit out a number. So the way that we have the affine decomposition, so the first box in the setup, well, we have something that really resembles the force vector. So we have this sum over these vector components, so these are all vectors, just like these guys were vectors, because both represent linear forms. And each of these vectors is again sought to be independent of our parameter, and this parameter dependency only shows up in that function theta. Right? That was the key property of an affine decomposition. Yeah, so during the online phase, we do not only want to get the affine decomposition of our stiffness matrix and our force vector, but now also from our output functional. And this functions in exactly the same way as for the force function. So once we have done that, and we have explored the solution manifold, and we have generated the reduced basis space, so V, yeah, okay. Then we would also have to pre-compute those components in that reduced basis system, as we see here. Yeah, so then again, this is exactly the same thing as for the force vector, because a force vector represents a linear form, just like this output is a linear form. Yeah, so also in the same sense, during operations, we can now regenerate the output functional for that parameter point in a very cheap way, because we pre-computed all the components. They're only a small n dimensional. We multiply those by the theta functions to obtain the vector that at this point represents the output functional. This vector. Yeah, so in the post-processing, after we've solved the reduced system, we can then get the output associated to our reduced basis solution, which is a function, u of x. We can evaluate that extremely cheaply by multiplying the line vector that is the solution by this solution, the output functional vector. So that was still sort of a missing piece of the puzzle that I wanted to connect here. Then the definition of compliancy kind of shows up here as well, and that makes exactly that connection here, that these are vectors and these are vectors. And a compliance setup is such where actually these are the same. So the linear form that defines our output, that is, would be the same thing as the linear form that defines the force vector. So that might seem a little funny at first, so I'll give you an example of that. Let me take one step back actually, and let's just be sure that we're clear on what we're doing here. Yeah, suppose that we're designing an airfoil and we produce a certain flow field. Then so this flow field enforces a certain traction along the shape of this airflow, and the output functional that we are interested in, so S of u of x, the output functional that takes the solution u, produces a number, would be, let's call this whole domain gamma, would be the integral over gamma of the traction vector, which is the stress tensor times the normal vector, over the surface of that element. Yeah, well, this is the normal vector. Yeah, so that would be an output variable. And very much in the same way, this is an example from fluid mechanics, but also if I were to design, I don't know, I have something that connects two components together, and I'm sort of designing a clamp here, I don't know, then we might be interested in the loads that this structure inflicts on its surrounding, or vice versa, the loads that the surrounding inflicts on the structure. Yeah, so that would actually be in a very similar sense, similar output, where now gamma would be the set of those, I don't know, either surfaces or points, depending on our setup. Yeah, so those are example outputs. Then specifically for the case that we are interested in, we're talking about a heat problem, and the output was the average temperature. So clearly that's also an output that we might be interested in. If we're designing a heat channel, what is the temperature at the inflow and the outflow? So what is the setup here, and why is this compliant? That's the last thing I want to address today. So what is the weak formulation of a heat problem? Well, you start off by minus the divergence of kappa times the gradient of phi is equal to f. We multiply by test function, integrate over the domain. Then we get minus divergence of kappa gradient phi times v is equal to f times v. We do integration by parts. Integration by parts on the first term, the left side. That gives us the integral over the complete domain of the Can I not? Of kappa times the gradient of phi dotted with the gradient of v. So this integration by parts introduces a boundary term, which we, for some reason, typically forget about in the beginning. And the boundary term is going to be kappa times the gradient of phi dot n times the test function itself, and the right hand side is unchanged. Now, what do we do next? We enforce the Dirichlet boundary conditions on the space. So that means that v is going to be 0, remember that, right? If you have a Dirichlet condition somewhere, that means that the test function is going to be 0. So this guy is 0 on partial omega d, the Dirichlet part of the boundary, which means that really all we're left with is this term on the normal part of the boundary. And on the normal part of the boundary, we have an expression for this guy. This was mu, I think, in on the normal boundary. So I can move this term to the right hand side because at this point it is data. And for the case that we are considering, we also have f is equal to 0. So I can move this to the right hand side, and the finite element formulation that we're actually solving right now in the homework is kappa gradient phi dot gradient v is equal to the integral over the partial omega n, the normal part of the boundary, where we're specifying an influx, times mu in times v. Okay, so that is our right hand side. That is a functional that takes a function v and outputs a number. Yeah, so let me address it, let me rehearse that. So the thing that we're interested in right now is partial omega n mu in v. So what kind of operation is that? This is an operation that takes a function v from h1 and produces a number, right? It's a functional. And that's the way that we should look at it. We never think about it this way because we always get rid of the test functions, but that's really what it is. Yeah, so this is a functional that takes a function and spits out a number. Well, we can introduce the v as right now this is still v of x as, again, the sum of coefficients times basis functions and then by doing so we obtain right now, if I substitute that and I work out, I pull out the effective coefficients, yeah? And this is what we define to be our force vector. Yeah? But what this encodes, again, is a linear functional. And how does this encode now a functional? Right now, what this is, this whole expression, this is a multiplication that takes a vector in Rn and produces a number. Yeah, so, and this still encodes the same information as long as we write our function in h1 as this sum. So the functional that this encodes is still taking, what it does is it's taking the integral over the domain of mu in multiplied by v of x. Now what in the homework assignment was actually the output that we're interested in? Well, we're interested in the average temperature on that boundary. So the output functional s of some function u is equal to the integral of u on that boundary. Well, and then I still divided it by the size of that boundary, which is 1 partial omega n ds. And that was actually already a given number, right? I think we're specifying here those are just 4. Yeah, so actually this number is nothing special. This is simply 4. Yeah, so actually let's just write that. This is 1 over 4 times integral of partial omega n of u ds. So how does that relate to this linear form? This is the linear form that takes the function v and spits out that number. Well, it's pretty much exactly the same, right? If I take L of u, that is, or S of u, that is going to be equal to L of u, this guy, well, I still have to divide by 4, and I also have to get rid of that mu in, so actually, so this is going to be 1 divided by 4 mu in times the linear form that is actually the right hand side. Yeah, so this is what is meant by a compliant output. That the output that we're interested in is actually encoded in the right hand side, the linear form of our weak formulation. That is somewhat of a limited case, not as limited as it might seem. So there are techniques of getting around this. Well, I actually just illustrated how to do that. You could normally just encode a new linear form as this in this affine decomposition. But there are some tricky things about it, because if it's actually compliant in this sense, you have certain optimality properties that's showing optimality of convergence that are kind of tricky to maintain if it's not in this case. And it's not as limited as you might seem, and that is because, well, linear forms in the cases that we are interested in, that arise from mechanics, they are often work couples, work pairs. Yeah, so we're multiplying stress and displacement because that's what defines energy. So at the points where we're prescribing a displacement, we might actually get a stress from the right hand side, or if we prescribe a stress, then we might get a displacement from the right hand side. So interestingly, it actually often does encode the information that we are interested in without actually knowing this beforehand. Yeah? So compliance is not that uncommon, is really all I want to say with this. Okay, and I think that's also all I wanted to still address today. That was the last thing. So then, yeah, so next week is lecture free. So we don't have a project session on Tuesday, and on Thursday I'm also not going to give a lecture. That's why the deadline for the project that you're working on right now is the week after that. So we still have one project session then, and the deadline will be in the evening. Yeah, so I'll use my time for the next week to write the individual projects, because after this project there's going to be one more project, and after that I think we've seen most of the important things. I think the projects have shown you the most important facets of all the theory that we want to talk about. So after that we're going to get individual projects that focus a little bit more on a certain detail that might also have some research interest. Yeah, so I'll write those in the next week. But for you it's lecture free. Okay, that's all I wanted to discuss today. Thank you for your attention, and see you in 2 weeks. Have a nice break.